So good morning, everyone. I welcome everyone for the fifth day, session 1. The topic that is lecture 13. The topic of today's presentation is post-plasma catalysis for ammonia production. We are going to focus more on catalysis. So before moving to the, this is the learning objectives. So what you are going to learn from this topic, understand the principles of plasma-assisted catalysis and its role in enhancing ammonia production efficiency. Analyze the mechanism of post-plasma catalysis and how it affects the reaction pathways in ammonia synthesis. So this is very important line. So affects the reaction pathways. So that means it's going to control the pathway. Identify the key catalysts used in post-plasma ammonia production, including the properties, application, and limitations. Assess the environmental impact and economical viability of plasma-assisted ammonia synthesis compared to conversion of rapid motion. Review current research trends and advancement in plasma-based technologies for sustainable ammonia. So, an outcome, we're supposed to know what is the purpose of using catalysts for producing ammonia through plasma technology, and why you are using that catalyst. So, what are the parameters we need to really think about in using that catalyst? What the significance of using catalyst with and without the catalyst? What is going to happen? Then, what is the right current research going on related to the plasma-based technology by using it? Maybe you can say noble catalyst or the green catalyst. So the presentation falls under 5 categories: plasma-based ammonia synthesis, plasma-assisted ammonia production techniques, plasma catalysis, post-plasma catalysis, and future direction and features. So what is plasma catalysis? What is post-plasma? And anything you plan before the particular activity happens. Suppose you are having the plan of doing something today before coming to the department, maybe the research college. So you have some kind of schedule today. I'm going to do this. Well planned, right? Then you are coming over here. Then you are going to do something, right? But you are not going to do all, I can say, the conversion in terms of here, ammonia generation happening, not completely, or not complete your task, right? Before 5 p.m. That is the office hours for Trichy. Then you will keep on extending the time to complete the job. So the planning at the end. Okay. So the post-plasma technology, whatever I can say, the process happening through plasma, we already seen in our laboratory. We didn't use any catalyst, but we are producing ammonia. So that is the plasma catalyst, I can say. This is the plasma method, right? If you are using, I can say, catalysis in the reactor itself, it's called plasma catalysis. If you are not using any catalyst in the reactor, but you are doing the further conversion of ammonia after it comes from the reactor, it's called post-plasma catalysis. Okay. And before moving to this, and there are several informations are available, we need to know what is catalyst. Anybody, what is catalyst? You come across, right, many way of adding some kind of constituent, right, even for preparing sambar, rasam, right, for preparing a biryani, right. So many ingredients are added. Right? So many ingredients are added. Suppose we are preparing a chicken biryani or mutton biryani, everything is consumed. What about the bone? What about the bone after consuming the biryani? It's going to be there. You cannot consume bone, right? You cannot crush the bone and eat. Okay. So if the material, assume that the 1 kg biryani you are buying from the shop, maybe around 50 to 100 grams going to be a waste for the bone. Correct. So if the bone acts as a catalyst for aiding the reaction, increasing the reaction rate, without mixing with the ingredients in the biryani, you can take out the bone. Even if you want to use the bone for multiple times, bone will be there for several days. You cannot break it unless the action needed for breaking the bone to the happen. Okay. That's why you are going to X-ray shop, or I can say MRI scan and all, the body scan and all, right? High intensity lights are possible, but nothing is breakdown. The minimum energy is supply. So The catalase is the substance which is used for increasing the reaction rate. So it will take part in the reaction. It will take part in the reaction. But if you are adding 10 grams of the substance for increase the reaction rate, after the process, after the ammonia generation, after the methane generation, whatever may be the process, or even for the emission reduction, three-way catalytic converter, then diesel particulate filter is a diesel engine. The catalyst coated on the filter is going to be remain same. So it will only increase the reaction rate and also reduce the activation energy of the process. Suppose the reaction happens at 700 degree or 1000 degree, the catalyst will reduce the energy level in such a way that low temperature, the reaction going to happen. The good example is, suppose if you are planning to go to Himalaya, Shimla, you can see there are around 30 tunnels to reach one side of the hill to another side of I can say the mountain. So if the hill is not there, there's a mountain, the tunnel is not there, how you are going to cross that, I can say the mountain? You need to climb up, then climb down. Right? That is the pathway. That is the only pathway. The good example for this GPS. Suppose we want to go to Chennai from NIT. That's not earlier, it is only one route, maybe I can say. Now it will be n number of routes. So how best I can reach the place within the short span of time? The catalyst will give the different pathways to attain your target. Different pathways. The good example is your GPS, what you are using. So in order to reach our destination from the starting point, it will find its own pathways. Suppose you are going for copper-based rubber bush, they are using ferrous Fe2O3. If you are using zirconia, if you are using rubidium, if you are using platinum, palladium, or combination of different noble metals. So that's the reason why there's a lot of catalyst research is happening. For this process to produce ammonia, what is the best catalyst I can go for at a minimum cost and get the maximum reaction rate and get the minimum activation energy? Okay. So people are saying Fe2O3. They said there are around 1,000 catalysts they have tried. They found that finally Fe2O3 is a good catalyst for carbon Bosch process. What exactly it means? That catalyst will give the minimum shortest way to reach the ammonia generation. Suppose if you are using Fe2O3, the reaction temperature is 100 itself, the process happens. Ammonia generation happens. That's not going to happen in platinum, it's going to happen at 300 or 400 degrees centigrade. So what is the minimum energy in which the process happens? Okay. So suppose if I'm assigning a job to Saravana to go to, I can say, Satram bus stand, right? I can give some food to take it, or without food he can reach that place. So what is already stored, what is the minimum energy needed, either by walk or by two-wheeler or by car. But you cannot, I can say, without giving food after maybe I can say several days, you cannot survive. So that is called without catalyst. So in order to aid the reaction, we need to use some kind of catalyst, find out the catalyst which is going to give the different pathway and which you are going to attain it, because we are going to provide the energy. We are going to provide the energy. And catalyst selection, not only for high reaction rate and also low activation energy. It should give low activation. There are different types of, I can say, catalysts are available. So every topic what you are studying related to the one is homogeneous and there is heterogeneous. Homogeneous and heterogeneous. Can you give one example for homogeneous catalyst? Even catalyst may be solid, liquid, gas is also possible. You should give the reaction. You should enhance the reaction. A good example is adding water with milk. homogeneity. You cannot separate out except one. Right? So homogeneity can be attained by mixing with solid, liquid with the liquid, liquid with the gas, solid with the gas. It's all coming under heterogeneity. Suppose we are going to buy a groundnut. Maybe they are frying it on groundnut. If you go to the roadside, they are doing it, right? They are using, I can say, the silica sand for heating, right? But the heat will be absorbed by the vessel first. It will be transferred to the silica sand through conduction and convection, right? Then the groundnut you are added not to the vessel, is added over the silica sand. Heat is going to be transferred. My question is, after the process happening, it is going to increase the reaction rate, and also maybe after 5 minutes we are going to take out. What about the number of particles present after the groundnut is taken out from the system? Going to be remain same. To prepare a sambar, you are preparing salt, you are putting salt. To prepare a tea or coffee, you are putting coffee powder, right? Sugar. Whether sugar is soluble. But what about the coffee powder? Heterogeneity. Okay. So we need to find out whether you are going for homogeneous, solid to solid, liquid to liquid, or I can say gas to gas. Here, solid to liquid, maybe the catalyst may be liquid, or liquid to gas, or I can say solid to maybe gas. Some combinations. We can say heterogeneity means you cannot, I can say, mix it both the things. Mixing oil with water. It's called heterogeneity. Probably. The good example is the combustion happening in diesel engine. Petrol can easily mix with air, the homogeneous combustion. Heterogeneous combustion, in case of diesel, you are using air, high compressed air, then you are over that you are injecting the diesel fuel. So heterogeneous combustion. Even then you are injecting pressure at 2000 or 2500 bar by using CRDA engine. The fuel will enter in the form of particle, not in the form of gas. Okay. Right. Then the catalyst, there are noble catalysts are there. The proven catalyst, noble, very costly, but reaction rates are high reaction rate. Platinum, palladium, lithium, zeolite. There are a number of catalysts are available, but here, if you are going for higher capacity, the usage of the noble catalyst will increase the cost of the reaction. So people are thinking about a bimetal catalyst. Bimetal catalyst. Or maybe people are talking about the catalyst, they are using green technology, green catalyst. But ultimately, whatever may be the type of catalyst, the ultimate aim in using the catalyst to increase the reaction rate, to reduce the activation energy. And catalyst is not going to be consumed. Catalyst is not going to be consumed. It is only export in the reaction, but only by increasing the reaction rate and reduce the activation. It's not going to take export in the combustion. Like oxygen reacts with the hydrocarbon producing CO2 and water vapor. It's not so. Whatever the quantity you are used, it has to be taken back. Okay. So you need to select the right catalyst. You can try the different maybe the local separate catalyst or mixing of two catalysts, bimetal catalyst or maybe triple I can say binding of the catalyst. You can think about that. But everything need to see the properties. Need to see the properties. Okay. So need to employ, I can say TGA, thermodynamic analysis. Need to find out XRD. Need to find out BET. Right? There are several, I can say, methodologies are there. Then you need to find out, I can say, why we are using different, I can say, equipments. There are equipments. TGA will give, we talk about the TGA analysis. So here the mass percentage. Here the temperature in degrees centigrade. So for completely burning out the particular solid material or liquid material, you are feeding into the furnace, maintaining, you can maintain that oxygen air environment, you can maintain it oxygen environment, you can maintain it nitrogen environment, also possible. So ultimately, the DJ will say, what is the temperature in which the process, if you use the catalyst, we can able to operate it. The operating window, you can able to find out from this process. Okay, from the TGA. So what is the safe zone? Suppose the mass reduction, assume that mass reduction is not going to happen. Maybe at some point, the mass reduction happens. For the catalyst, for fuel, it will be different. For the catalyst, there will not be any loss in mass. Suppose you are using 1 gram of catalyst for testing the TGA, same 1 gram is going to be there after, and what temperature is going to be retained. But it's not safe for the fuel, I can say, for liquid fuel or the solid fuel. So we need to convert it. Whereas for other fuel kind, how much the temperature in which 100% the fuel I have used for finding the new fuel, the solid fuel, biomass, or maybe the liquid fuel, any liquid fuel. What is the temperature at which I can able to completely evaporate it, completely convert it, combust it, or evaporate it, nitrogen, in terms of nitrogen mode. So that is also possible from the TGA. Exactly, it is going to give the structure. The structure, okay, maybe you can say the particle size also we can able to find out from the X-ray diffraction method. BT is the method in which the absorption, I can say, maybe you can say absorption and the desorption is given to study. So normally they are using nitrogen as a medium to absorb and desorb for the particular catalyst you are going to use. Why they are using nitrogen? Because it's igniting stage. So along with this, people are using scanning electron microscope, right? TEM. So I am not a catalyst person, but there are several catalysis methods people are using before using the catalyst for the particular process. So here from the catalyzation itself, they found the property, then there is a confidence that okay, this catalyst will work good. And also the most important property is called reusability of the catalyst. Reusability of the catalyst. Suppose the catalyst can be used for, I can say only once or maybe used for 10 times you can use it. There's no drop in the yield. Then if you use it for 1,000, 100 cycles or 1,000 cycles or 10,000 cycles, then accordingly the selection of the catalyst is also. The reusability of the catalyst is also very, very important. But at the initial time, maybe for ammonia generation, for using one catalyst, assume that the ferrous-based catalyst giving maybe I can say 90% yield. Maybe for next 10 trials, same yields you are getting. Maybe there is a drop in, there is a drop in yield for using the catalyst again and again. But we need to ensure that how much time the catalyst can be used so that the yield what you are getting, at least it should not be equal to the without catalyst. Suppose without catalyst you are getting 50% yield ammonia, but you can try the number of times using the catalyst up to maybe 60% or something. So going below, very near to the without catalyst, there's no meaning in using the catalyst. So and also the catalyst part, catalyst poisoning is one of the issue. Doesn't related with like it is going to poison the environment or something. Whenever I can say when you are using the catalyst, the absorbed particle over it, it has normally it has a porous in nature. It is going to absorb, and after some time, that whatever is absorbed, it has to be dissolved. It has to be dissolved again. So if you are assuming that there are a few gram of the nitrogen producing ammonia is going to be absorbed over the surface. Absorption and absorption difference. Absorption means going to penetrate into the core of the particle. Absorption means it will be coated on the surface. Okay. Now, if the desorption is not going to happen, after some time there is a blockage of the particular porous material. Okay. So that is going to create a poisoning effect. That means Instead of 100, I can say codes. Suppose you are because of the very poor desorption, the 10 I can say porous codes are closed. Only 90 codes are active. That is going to affect the performance of the catalyst. So the concept called regeneration. We talk about the catalyst. The regeneration is very important. You need to ensure that the catalyst deposit, whatever is deposited over the surface of the surfactant material what we are using, base material we can say. We are not going to use assume that the catalyst is coated over some cylindrical ball or spherical ball, but all the volume is not covered with catalyst. What we want only surface reaction. So out of the 100% volume, we may have 1 to 2% the surface coating. Remaining 98% is called base material. Base surface, I can say. So we need to regenerate it. So means at one particular temperature or maybe the pressure, whatever it is dissolved, absorbed, is not going to be dissolved. We can do the recycling of this one. Ensure that again you are getting 100 porous codes. So this is basic for a catalyst. Catalyst will leads to, I can say, will find out the shortest pathway in which our desired objective is attained. Desired objective. So here is a very important graph. You can see here there are different methodologies are available to produce ammonia. Low pressure plasma, non-equilibrium atmospheric plasma, then Haber-Bosch thermal process and thermal process. So here you already come across the non-equilibrium atmospheric plasma. We already visited our laboratory. Thermal plasma we will be taking to explain this thermal plasma in our laboratory. So this is high temperature, right? High electron intensity plasma. The non-equilibrium is low temperature, high electron intensity plasma. So you can see here the x-axis talks about the pressure, then the temperature in Kelvin. So in order to operate, in order to convert, I can say, from the raw material to the product, you want to go for a high temperature plasma. The temperature is varies from the order of, maybe I can say, varies from 10 power 3, that is 1000 Kelvin to, I can say, 10,000 Kelvin. That is the operating range for high temperature plasma. The pressure is about 10 power minus 1, that means less than atmospheric to the, I can say, this is the atmospheric pressure. Then it goes up to 10 power 1. Okay. The pressure also is going to be increases for high temperature plasma and temperature also and pressure also increases. The low pressure plasma, the range of pressure is 10 power minus 2 atmosphere to 10 power minus 4 atmosphere. With 1 atmosphere is equal to 1.013 bar. So 1 atmosphere is equal to 1 atmosphere is equals to 1.013 bar. So 1 bar is equals to 10 power 5 Pascal. It's also equals to 10 power 5 Newton per. So when you talk about the low temperature plasma, I can say low pressure plasma, the pressure range is 10 power minus 2 to 10 power minus 4 atmosphere. Then for non-equilibrium plasma, the pressure range is P means pressure, T means temperature. So here the low pressure plasma, the temperature is T in Kelvin, you can say, which is in the order of 100 to 1000. So for non-equilibrium plasma, the pressure is in the order of 10 power minus 1 atmosphere to 10 power 0 atmosphere. Or I can say 10 power 1. 10 power 1. The temperature T is equals to about, I can say, nearer to slightly more than that. This one, maybe I can put temperature is in the order of maybe 100 Kelvin to 1100 Kelvin. So when you talk about the Haber-Bosch, as you all know that the pressure is in the order of or I can say greater than 100 atmosphere goes up to 350 bar. Then the temperature is in the order of, I can say, about 450 to 550 Kelvin. Which, with respect to this problem, it comes to around 7. So we'll move to the next one. There's a thermal plasma. That is thermal plasma. So the operating temperature is in the order of 10 power 3. That is 1000 to 10,000. So you need high, I can say, high current rather than the high voltage for thermal plasma. So here, then the pressure is in the order of, I can say, 10 power 1 to 10 power 1 to 10 power 2. Then we have different methods of producing ammonia. Maybe we already know that I can say Haber-Bosch and through gold gasification method we can go for it. Gasification we can produce hydrogen, CO1 synthetic gas. Can say. Now people are using biomass to produce the synthetic gas. From that you separate out the carbon monoxide, produce hydrogen, which can be used for producing ammonia. And maybe methane reforming the method, the electrolysis. Then we have another two methods called Birkel and ID process. It's a multiple step nitrogen fixation reaction that uses, that is earlier days, 1900 to 19, I can say 10. This method was employed. Maybe they can say it's producing nitric acid, water. So they and also it produces in terms of energy consumption, very high. Then they have eliminated this process. And around 1920 to 1925, we can say they are going for the Frank Carlo process. This is also the nitrogen fixation process. The action of calcium carbide with nitrogen gas in the reactor about 1000 degree, continue to produce a useful chemical feedstock. But the conversion rate of I can say hydrogen and ammonia compared with Haber-Bosch, this is not going to be attained at their target, particularly industry. That from 1925 till now, you can see that till now, I guess they put after 2050, they are claiming that Haber-Bosch going to continue because the green energy method, what we are suggesting to, I can say the electrons method, what we are suggesting to produce hydrogen, it's not going to comparable with the Haber-Bosch. The only problem with the Haber-Bosch is highly energy intensive than the CO2 generation from the reaction. Then the CO2, we are going to get nitrogen oxides also. So if you're able to do some kind of initiative for Haber-Bosch, the minimum energy consumption by eliminating CO2, then this is also competitive to the current electrolysis process. So here Haber-Bosch, we know that. So natural gas converting into, I can say, carbon dioxide and hydrogen. Then hydrogen reacts with the nitrogen comes from the air separation unit. We are putting, I can say, ammonia along with CO2. CO2 we're not capturing, that is called gray ammonia or black ammonia. If you are separating out by using some carbon capturing system, then if you are producing, then you are able to produce many things from CO2, phosphoric acid, methanol, then other synthetic fuels also. If you are able to use some kind of catalyst, that's why the catalyst plays a major role. So if you use some catalyst for not only for producing ammonia, some catalysts also aiding for formation of other products also. So today morning I spoke with the person, chemistry professor Carve, he is the person doing a lot of research in I can say catalyst. He also suggests me to focus on some kind of coating on the electrode. So kind of coating on the cold plasma electrode what we have used, right? And also he suggests me to change the I can say shape of the electrode. So circular and cylindrical we are using, and it can also he is suggesting that, sir, you are not producing carbon dioxide, but even the carbon dioxide comes out, capturing, you convert it to some form of the fuel, combustible fuel by using the same catalyst. So there's because the ammonia wants the temperature of around say 450 degrees centigrade, pressure is around 100 to 350 bar. Even to reach that pressure, even at 100 bar pressure and temperature of 100 degree or 200 degree, other products reacts with CO2 also will come up. So try to tap out. Suppose the Lakshmana is working on biomass gasification. It's not only producing carbon monoxide and hydrogen, CO2 also comes out. He's saying that capture of the CO2 and convert that CO2 into a combusted product into combustible product. So some catalysts are available. So he promised me to, I can say, work on that. Okay. And plasma catalyst ammonia production and electrolysis. And we have a anode and cathode. So anode produces H plus, cathode, I can say, along with the electron, combined with nitrogen, produce ammonia at the electrolyzer outlet. Okay. And without, and also you can add some kind of catalyst. This is called plasma catalyst. You can think about some kind of catalyst coating the surface of the electrodes. That is also possible to enhance the hydrogen. Maybe in the anode side, you can use some kind of catalyst which you are going to increase the more yield of nitrogen, because the amount of energy you need to split nitrogen, triple bond into single bond, the catalyst, some catalysts are really supporting to reduce the activation energy. So you ask me to focus on that part also. So with the minimum energy level or the same energy level, the ammonia yield in terms of ppm comes out from the reactor is going to be enhanced by bringing catalyst either in the reactor itself, or coating, or in the fluid itself, or post-treatment. So another one is the photocatalytic ammonia production process. I think this also we have explained in the it's a tutorial class in the laboratory. We are using UV rays to, I can say, create some kind of vibration energy. Normally, right? So you do not to split water into hydrogen. By using UV, you can able to dissociate, or you can maybe use some kind of activation so that it will be create some kind of vibration or splitting. Okay. So then I have separation unit, they are producing nitrogen. So both are in active state. Then you can send those active state of hydrogen to the catalytic zone, where you are going to employ the plasma energy to combine this nitrogen activation and hydrogen activation into ammonia. So there are many things. What is the facility what you are having, surrounding is having, it is only basics. So we are having, I can say, producing ammonia. We are claiming that by varying the parameters of intensity of, I can say, energy or electrode gap or nitrogen flow and other things. These are basic. Still, we can explore many things. So we can get the optimized condition. In that optimized condition, you can think about bringing catalyst inside the reactor or outside the catalyst. So that has a lot of benefits. And also, he's suggesting me that if you provide some kind of catalyst on the surface of the electrode, or maybe the post the treatment side, the element comes out other than the ammonia, NH, NH2 or nitrogen. By using catalyst in the reactor itself, you can, the conversion is going to be very high. Instead of NH to be converted into NH2, it will easily can form NH3. So that also we need to really think about. And also he suggests me that using some catalyst, ammonia, before ammonia conversion, NH and NH2 conversion happens. So you can use some kind of catalyst. For that energy, it is possible to produce ammonia. So it will increase the yield. The electrochemical conversion, we already studied like this one. So this is the plasma technology. You can use any kind of inert gas to ionize the gas. So here the concept what we are using is the non-equilibrium. Non-equilibrium. That means the temperature of gas and the electron temperature, if it's not remains same, it's called non-equilibrium. That's the hot plasma. The electron temperature and the ionized gas temperature remains same. It's called, I can say, equilibrium. So in hot thermal plasma technology, we are using equilibrium conditions. Here we are using, I can say, non-equilibrium conditions. So here we are using plasma. We're going to create from the electrodes. Then in between the, I can say, cathode and anode, the water is there. Then also the catalyst may be above that surface. So you can able to increase the reaction rate and reduce the activation energy of the process to dissociate the maximum amount of water into hydrogen. It will increase the yield of the. Not only for producing ammonia, other constituents are forming, right? Other than the hydrogen or in terms of nitrogen, other traces NH or NH2 or N2, the catalyst will further, we can say, convert into our expectation. So this is the nitrogen-nitrogen reactants reaction mechanism, how the nitrogen is converted into active state, how the ammonia is formed, right? So this is the general plasma technology. By using the catalyst, right, we can say how the reaction happens. So nitrogen is going to be absorbed on the surface of the catalyst. Then we can see here, then that will during absorption and desorption, the minimum amount needed. So whenever it finds the most active species near to the nitrogen, it will form the nitrogen, produces NH or NH2, and then finally. So the catalyst will enhance the reaction rate and producing the minimum energy to form the ammonia. So synthesis of the catalyst plays a major role. You need different furnaces, right, to produce the, I can say, single catalyst or the bimetal catalyst or different combination of the catalyst. You need some kind of basic system to, I can say, produce the catalyst. As I already said, there are different parameters, right, which is going to be studied for analyzing the catalyst. So this is the simple, I can say, the catalyst, how the catalyst is going to be takes part in the and supporting of the plasma energy in terms of forming the ammonia. You can see here hydrogen is coming. Nitrogen is the red in color, nitrogen is blue in color. When it comes to the catalyst surface, and the plasma is passed on to the catalyst surface, then you can see here the nitrogen is absorbed over this. Similarly, some kind of catalyst is also going to be absorb the, I can say, hydrogen comes out from the electrolysis process. Then it's going to form, it's going to helpful for, I can say, forming the ammonia. So this area we need to really explore it, and we need to make sure the people, those who are currently focusing on that research. This is very important graph. You can see a different methodology. Slave Professor who also discussed that the radio frequency, microwave, or different methods in which we can be able to, I can say, actively, I can say, the catalyst. How the different energies can be used for activating the catalyst. So among this, you can see here our target. This circle talks about our target. Our target is to consume 1 unit of electricity. I need to produce 100 grams of ammonia. Okay, and the ppm concentration is around 10,000. Okay. So among the different methods suggested, you can see here, radio frequency is going to be plays a minimum role in producing the ammonia. That's microwave. So I can say it's next to the radio frequency. Then you can see a dielectric barrier discharge. That is a method we are using, right? We are using for producing the ammonia, that is plasma. The same method also we are using for producing the different constituents from the hot thermal plasma. Among these, you can see here the dielectric barrier discharge pulse method and the dielectric discharge alternative current method is going to produce the maximum amount of ammonia with a given power input. Okay. So catalyst synthesis, you know that supporting material over there you are going to add the different, I can say, elements. One can support for nitrogen. You can see here the ruthenium is going to split the nitrogen N2 into triple bond into single element. Similarly, some kind of elements used for supporting for hydrogen also, dissociation also. Maybe it's called cesium, and we are going to absorb the different elements, nitrogen. Maybe over the ruthenium, it's going to be absorbed. There is cesium, and it is going to be absorbed. You can see here. So in order to use the ruthenium completely, it is going to increase the cost of the process. What people are doing is, so they are using a low-cost material, there's a supporting material to coat over it. So this is the base material, magnesium oxide or aluminum is a proven base material, right? Then ultimately, we can just example is we're applying powder, right, over our face. Right? So this is the skin, this is a supporting material. So this, right, if you're going for small micron size, small mm size thickness sufficient. So for I can say pretty well increase the thickness of the, you can say, coating. So here, how much the optimum thickness of the, I can say, catalyst can be coated over the base material. It's also a measurement. So putting 1 micron is going to give the same performance by putting, I can say, 10 mm thickness, right? It's going to increase the cost. So we need to find out the reusable cartridge with a different coating thickness. Different coating methods also there to coat the highly, I can say, the noble metals over the surface. Suppose the total weight of the catalyst is around 10 grams, right? Assume that. By keeping ruthenium buying 10 grams, it's going to be filled in terms of few lakhs. So here, what you need for the thing is only you need 1 gram of the ruthenium cesium based catalyst. Then 9 gram you can go for magnesium support. It's only low cost only. Then what is the data? You need only surface treatment. Not, I can say, not we are going to allow into the core of the surface, right? So going to be absorbed at some temperature return, it's going to be dissolved. Okay. So this is the in-plasma catalyst and the post-plasma. So the catalyst is mounted in the reactor itself. It's called in-plasma catalyst. The catalyst is out of the, can say, assume that from the reactor, nitrogen comes out or hydrogen comes out, or it's nitrogen, NH or ammonia is coming out. Further, you want to increase the yield of the catalyst. It's called post-treatment. The way we are doing for an engine, right? Three-way catalytic converter to convert CO to CO2, then NO to NO2, right? Hydrocarbon to water vapor and CO2. Same way, the further unreacted species of hydrogen can be converted to ammonia by keeping it post plasma catalyst. But what the disadvantage is, you need high pressure energy to pump it. So this is going to add the cost of the system. Is there any method to produce ammonia in the system itself? Then we can say, then we can think about it. That's why I said, like, you want to reduce the emission in the engine itself, or you want to control the emission and the exhaust. The controlling and inlet, right, it will going to save the fuel economy. If you keep everything in the exhaust and it's going to create obstacle, it's going to increase the vehicle space and also increase the pressure drop in the exhaust. So back pressure is going to happen, it's going to increase the fuel economy. Same way, this is the post-treatment method, but if you find out some kind of green method in boosting the ammonia yield by using this method, very much appreciable. So various methods, yesterday you Professor discussed about the chemical looping, right? So chemical looping is nothing but I can say you cannot produce the ammonia in a single I can say reaction itself, right? What is coming out when you pass on the hydrogen or nitrogen into the catalyst, you may not produce the ammonia 100%. So what may be the other constituents other than the H or N or NH or NH2, that may be taken in the next loop, where we'll ensure that before it goes out from the reactor, the ammonia conversion is happening. It's called chemical loop. The reaction mechanism happening from the hydrogen source is hydrogen source in water, how the reactions are happening, right? So how the reaction happening in terms of photocatalytic reactor in the using a UV radiation. So for all the methods, need to say that what is energy intensive process, maybe by using photocatalytic or maybe DBD or DBD with pulse or DBD with ESC or radio frequency or microwave. Ultimately, need to produce ammonia at low or in. That is our intention. And also, the catalyst is going to support for, I can say, increasing the yield of the particular process. So DBD, the proven catalysts are ruthenium, magnesium oxide, and carbon nanotube. The promoters are, I can say, cesium, potassium, and barium. The ammonia is about 2.4%. Efficiency, energy efficiency 2.3. So similarly, microwave radio frequency. There are a number of catalysts to support the, I can say, microwave or radio frequency. But what is available in the particular literature that I have listed? You can also try about the new catalysts also, new maybe I can say aluminum oxide and alpha aluminum and ruthenium. Similar to that, you can find out some green catalyst which can also lower in cost, but it can provide the efficiency of convert the efficiency of nitrogen to form ammonia. It is equal to the noble or low cost, I can say, bimetal catalyst. That also is lot of research. Okay. So how the ammonia formation happens with respect to the active catalyst and supportive catalyst. So the mechanism. So the combination of plasma with the catalysis for synergizing and decomposing ammonia is an attractive route to produce carbon neutral fertilizer and energy carriers conversion in hydrogen to plasma catalyst. The synergetic effect between plasma and catalyst. Synergetic means combination of these two. Okay. So if we are using only one, I can say, system that is only plasma to produce ammonia, it's not an energy system, we can say. Synergetic means multiple components are added into that to produce the required product. Suppose you are using biomass to produce synthetic gas, it's not called synergetic. Suppose you are using biomass along with e-waste, either plastics or some waste material added to the process to increase your yield, that's called synergetic. It's called energetic effect, it's called synergetic. Multiple of energy components are added. We tried because we had an experience of trying energetic effect and synergetic effect. We come across and we used biomass for one of my scholar Ridesh and this problem of water formation and separation. We got very good, I can say, problem. And in order to solve that, and also the energy calorific value of the fuel is also about 20 megajoules per kilo. But it is approximately, I can say, nearer to 50% of the calorific value of diesel or petrol. And but we need to increase the flow rate of the oil, or maybe the oil comes out from the pyrolysis, or maybe the gasification, we can say. And in order to avoid that, what we tried is we tried biomass along with plastics, waste plastics. So low density polymer and high density polymer also we worked on it, and we worked on low density and by using a microwave reactor. I will explain that. Maybe you take the laboratory to explain. And we have combined the biomass with plastic because plastic's calorific value is more than diesel calorific. Diesel is around 45.8 higher calorific value, whereas plastic is around 48.5. So by mixing, blending the low calorific value raw material solid into, I can say, plastics, we have come up with bringing the different synergetic effect. We attained a very good yield. That is comparable with diesel. So we have used the biomass and plastics in the microwave reactor. And by using microwave absorbent, we have used activated carbon. And the water particle is already, the professor mentioned that it's going to absorb the, I can say, microwaves. And we got very good fuel, but that is replaceable to the diesel. Very much replaceable because the calorific value is about 46 point something. So that means the same fuel tank you can use it and we can run the engine. Viscosity also we came to know that the plastic viscosity is very, very low. After mixing with the biomass, the viscosity is what we need for diesel is 1.8 to 2.1 CST. At mm square per second, I can say. But we are getting very near to that, slightly lesser than the diesel viscosity. We found that. So we also, I can say, tried the engine very well. I can say the emissions perspective because of the residue of sulfur and lower, I can say, carbon content nature. The amount of carbon dioxide comes out also going to be very low. So different, I can say, ammonia generation systems starts from 1929 to 2023. I can say. So after an excellent ammonia generation, 2023. A record of ammonia yield of 148.8 milligram per hour per square centimeter. So this is the maximum yield obtained by the professor. And there are several technologies are emerged from 1929 to 2023. You can go through the literature and you can able to explore it. But you can find out what will be the yield at 1929, what will be the yield at, I can say, 2023. So we need to maintain the same energy level to increase the yield, or we need to reduce the energy input to get the yield what we are getting for the proven one. So we need to really work on it. So the catalyst plays a major role in minimizing the energy, minimizing the reaction, increasing the reaction rate by consuming very minimum energy, and also the chemical looping by providing the particular catalyst not only for increasing the ammonia yield and also supports for the unreacted components comes from in the form of nitrogen and nitrogen or combination of this. So also people are working on. Okay, so number of publications comes out in terms of from 1980 to 2020. I can say DBD, you can see here the number of publications comes out from trial with barrier discharge is increasing from, I can say, from the year of, I can say, 2000, now it increased to 30 approximately it comes up. So that means people are accepting that the trial with barrier discharge, the plasma generation, and that's the reason why we have a lot of publication comes up. By making use of this, the recent area, we also showcase our ideas in IIT Hyderabad in the inventive program. Our work was very much appreciated. The great work of, I can say, so Uday Kumar. And I hope this may be happened for our surrounding also in the terms of handling gold plasma. So there are different, I can say, directions of which directions of research funds are available. Now, if anybody wants to work in the green hydrogen, you will get a fund very easily. A lot of funds are they are pumping like anything across the world. You can get a multi, I can say, international projects also. You can get a supply for European projects, India and European projects. You can combine with, except the UK, you can combine with any country. Because Denmark is the leading, Denmark, Norway. We were thinking that the UK is no, it's not so. For harnessing the renewable energy, other than, I can say, UK, some other countries play Denmark and Finland and Norway, static like everything. So if any call comes, you can try to contact. The way I contact the professor for conducting the ER program, and you can conduct it in a joint collaboration. Whenever you apply some kind of joint projects, international projects, the people from the abroad will visiting your place, and you are also have the chance of visiting their place. Total expenditure for travel and accommodation and all other expenses, and only one thing is, some of the call will support only for travel and the daily expenses. You must have the minimum basic estimate. Suppose the call like MNRE, CSIR, then ISRO, like then Ministry of Mines, Ministry of Defense, DST, they will give not only for travel and other things, but it's only within, I can say, inland, only in India. And you can buy very good equipments. We have submitted a proposal, it was sanctioned, but about 1.2 crores of fund we are going to receive from the DST to produce the green, I can say, electricity for the people of SST but Thurayu. All are renewable, biomass, what is locally available. So think about what is available. See, we are also a capital, what is available to us, please have it. Don't allow me to buy something from the house. So what there are several sources available. No, you harness. The human catalyst, you can convert it from what the available material is. So we are making use of the action. So there are maybe every Boston, right? The message and all. Huge numbers of reactions are coming out. We are collected and converted into activated carbon because it has a calcium oxide, calcium carbonate. So it's a calcium carbonate. If you calcinate, you will get a calcium oxide. Okay. So calcium oxide we can use as a base material from the waste. We take it to the furnace, we calcinate at 900 degrees centigrade, we get calcium oxide. So over that we are using the activated carbon, impregnated. The metal we have taken from the e-waste, then the activated carbon we are producing from the biomass. That even for calcination, to connect to the not to the grid, to the solar or the wind, so it's called green catalyst. So these are the references I have used for preparing this PPT. Thankful to Uday Kumar and other students are supporting in bringing the information in the form of PPT. Thank you so much. If you have any questions, you can. Maybe we can take it to the other facilities, right?
Yes.
Maybe you can.
We have a tutorial system.
Tutorial system. We can run it. So before taking them, you can practice and ensure that something is coming out.
Yes.
So by keeping them and saying that it will come or something like this. So we will need to prepare before the process. We'll take it to the power limit, how the field testing are there. We'll take it to the ultrasonic also. How the ultrasonic process is going to helpful for preparing the bio, PL and other things. And we will take it to the microwave facility also for producing the oil from the solid or from high density liquid into low density oil. And we will use both biomass separately or combination of biomass and plastics in various combinations. We can try to run some micro reactor. And the thermal plasma reactor also, same material you can try with thermal plasma. How best in this better than the microwave and the electrical. So we have electrical reactor, microwave also, and thermal reactors also there. So why we are preferring thermal? By seeing the reaction, you can able to understand. Thank you so much.